Thank you. Thanks so much. Yes, I'd like to tell you about a body of work we've been doing the last couple of years on developing fast, robust statistics to study large-scale clustering. And so I had the wonderful introduction from all the previous speakers, in particular Istvan, in the last session. And it's joint work with a large cast of characters. It was mostly sort of started when Arka Banerjee was a postdoc with us at KITP. And so, yeah, let me tell you about it. And it's going to be a very sort of simple setup. So, you know, in our mind, the minimal problem we're going to be talking about is we have a volume, you know, and it might not be regular or something. We have a whole bunch of data points in it. For our purpose today, all the data points have exactly the same weight, and they're not uniformly distributed, and we'd like to somehow specify in an efficient manner, say something about this clustering of what is the pattern and how are these points distributed, and do it in a way that fulfills a few metrics. There's a couple of things in the goals we have here is, you know, we really want to bring out the information that is in how is it non-uniform. And what's also going to be helpful is, and we've seen many examples, of course, in cosmology, we really have this bias that we think about, that there's an underlying continuous field we think about, out of which we're sampling, and that's the points that we then find. And so that's also a nice property that would be good to keep in mind if we, you know, have that for our tools that we'll be developing. And of course, it's the whole context is really about survey science, like having so many things we're observing in the universe. How do we relate it to our theoretical ideas of how structure forms in the universe? And so a few of the metrics and sort of goals and things I have in mind for this is, obviously we want it to be informative. It should be a useful, whatever we measure, like in the quantities we express, it should be informative, right? It should also be interpretable in the sense that we as human beings can argue about it, reason about it, and we saw a nice example about two-point statistics earlier, that it's not always easy to interpret it, or we can have different interpretations on it. We want it to be predictable, so all those functions we'll be measuring. We also want to have a framework that we can take our theories, predict them. It should be robust, so that means if I have some outliers, they don't really change everything about it in our measurements. And they should be really fast to compute because we have so much data and we'll be doing it all the time. And then, you know, in reality, we do so much, you know, MCMC inference. So very often we do these measurements also on lots and lots of fake data. So it better be fast. And then if we can avoid it, obviously we don't want to throw stuff away. And averaging usually is a way of throwing information away. So if you can avoid binning and averaging, that tends to be a good thing. And you might have some sort of theoretical biases of, you know, what the sort of symmetries of your problem are, the symmetries of the theory underlying it. And ideally, your statistics will also respect that. And then the other part, you know, that's important to me is it should really have a minimal number of nuisance parameters. There shouldn't be much smoothing scales, parameters, choices of bin widths or bin sizes, or and that's a very personal thing because you have to, every parameter you do, you have to constantly check and recheck. And if I change something, does that parameter still have an influence? And it's just, you know, eventually you're going to get lazy because you don't want to check anymore. So if you are sure you actually don't need them, it's great not to have them. And yeah, so I think we can agree on that. And I mean, perhaps for the question period, you want to think about, you know, what's missing? I mean, what else should it have? And so I'm advertising this first paper, and then I'll say more about the others. And so I'll just tell you about this procedure of what we're recommending is a good way of organizing your data. Is what you do is, so our red dashes here are our galaxies, and what we'll do as a procedure is we throw down random points now, and so these are our blue points, and for each blue point, we're going to find the nearest neighbor in the data. So we have a random point, and then we found the nearest data point, and then we just record how far is that one. or how big is the volume of the sphere that is made, that has that radius of that distance to that next neighbor. So we can do that 1 billion times. So now we have 1 billion points to be thrown down. We made 1 billion measurements. For each point, we found its nearest neighbor. So that's great. So then we just sort it. We sort it as a function of the volume of the sphere, the measurements we had. And so now, and then we divide by the number of measurements we did. And so what we would call this is an empirical cumulative distribution function, because the probability is 1. So all my measurements were that largest value or less. And it goes down all the way to 10 to the minus 9, because I made 1 billion measurements. So each measurement is one little tick mark on the y-axis. And so these CDFs, they always look very boring. I mean, they're always just S-shaped, and then you plot them linear, it's like, oh, what a drag. So let's not do that. Let's plot them logarithmically. That's nice because remember, our measurement was down here at 10 to the minus 9. We saw a whole tail of measurements that might be interesting. So let's plot the CDF on a logarithmic scale. Yeah, but then it still just goes to 1, and we miss everything back here. So let's just subtract 1 minus the CDF as soon as we hit 0.5, because then we can still see the tail back here as well. And so now we have something, it's kind of like a PDF. It's got both tails, and it's sort of higher in the middle, but it always goes to 0.5. But what I like about it is I don't have to do any binning. Like, I didn't have to choose any bins, and in fact, whether I did 10 to the minus 9 or 10 to the minus, 10 to the 9 measurements or 10 to the 8 measurements, it's always exactly the same thing I will get up here. So that's a nice aspect. Now, the cool thing is what we inadvertently did, we actually calculated the probabilities of having 0 points in a volume of a given size, because we found the first nearest neighbor. So the fraction of spheres that I found that did not contain any other point, that's my first nearest neighbor distribution, and that's the void probability function for the people that knew about this. But we also did it for all the other Ks. We went up to thousands of Ks. We did it all in one go. And so now we have the first nearest neighbor, second nearest neighbor, third, fourth. The nice thing is if I subtract one from the other now, so if I take the second nearest neighbor, which is all the volumes that contain at least 1 point, and I subtract from it the one that contains no points, then I get the one that has exactly 1 point. And so these are these P of Ks, and it goes as the counts and cell distributions. But now look at this. So this is the probability of finding 0 points as a function of volume, but I got all the volumes in one go. And so previously, when people do counts in cell, they throw 1 million spheres, and then they count the fraction of the spheres that had 0 points in it. But they had to do it for each size of the sphere they wanted to do it. And so here, this is much, much more efficient to just get it all in one go. That's sort of the nice advantage, because you notice we haven't averaged anything, we haven't binned anything. We just reorganized how we think about our data. Now we have access to this lovely information. So if I want to make a PDF, then think about, okay, let's imagine I'm smoothing the field at 10 megaparsecs. Then I can just read off, this is how many bins I will have that have 0 points in them. This is how many bins I will have that have 1 point in them, 2 points, 3 points, right? So I'm building up my PDF, actually from your side, from the low densities, I'm building that up, but I already measured all of it, and I don't have to do any smoothing ever. It's just part of the probabilities of how these spheres fill my volume. So it's just a very, anyhow, so I have a lot of fun with this because you see the way the functions are, and because it's a CDF, I can just use a linear interpolating function spaced in log here. So I need very few points to summarize, again, all the measurements if I want. And then I can work extremely efficiently my code with it, because I can do subtractions, I can integrate things, differentiate, whatever I want. It's very nice. It has no intrinsic extra noise to that. And that's sort of one of the things that Istvan said already. The key part people get excited about is that that all this information in having the PDF smooth on all scales depends really on all the correlation functions. And so now you obviously get beyond 2-point information, by just looking at all these PDFs at these different smoothing scales, and we have the simple way of getting it back out in one go. Now for Gaussian fields, you can write down exactly what you would get. You have two parameters. There's a mean density, and then you have the variance as a function of the volume. So you write down the function for that variance, and you get these two probabilities, your first nearest neighbor distribution function and your second nearest neighbor distribution function. And that characterizes everything about that field. So I wrote a little code where I actually had Mathematica spit out the formulas for me to give you the first 20 of those P of Ks, giving exactly, finding 10 particles, galaxies in volumes of this size. So we have a few things. It's it's clearly robust. It's actually very fast. We use a KD tree. It's 2 lines of code in any of your favorite languages, because it's I create a tree that stores all your data, and a second line to query at the points you care about, random points, or you can do a uniform grid, and then you can make maps, which is also really fun. And we can get into that. Say again? In assembler, it takes more libraries. That's correct, yeah. But all the languages you might use, like Python, Julia, like they all have fast implementations, even Mathematica. Okay, so what do these things look like? Just to get a little feeling, a Poisson distribution would have this peak CDF. Particles in a Quixote simulation, taking 10 to the 5 particles out of a gigaparsec volume, the dark matter particles would have this distribution. You see how the tail changes, how the mean changes. And then the halos you see are more clustered. And that's how the peak moves over, and how the tail changes, how you end up with more voids. And here's the same expressed in this P of K. It's just for a few of them, the lowest ones, focusing on the lowest density. And be careful of the time, but here's an example, just contrasting the information you have in the 2-point function, where in the Quixote simulations, we have hundreds of boxes at the same cosmology, so you can take the mean 2-point function and really just get the mean extremely well. In the 15 dotted lines here that you see in the background, there's just 15 realizations, where we then divide by the total mean of the hundreds of boxes, and you see sort of a rough scatter of box-to-box variations for this 2-point function. And then I compare the one at redshift 0.5 with the one at redshift 0 for one realization, just to see, could I make out the difference of the 2-point function of the most massive 100,000 halos at redshift 0.5 to the one at redshift 0. Is that kind of, yeah, maybe I don't buy it, like, right, it's sort of kind of in the noise. We do the same thing for the CDF, and there's a very strong, clear feature that's way above, below your box-to-box variation. And that's just sort of making a point of, okay, it looks practical on a very idealized experiment, but that's how we start. And here's sort of a Fisher type forecast for doing this for cosmological parameters, again with the 100,000 points. And essentially all it's saying is that the purple one is much better than the orange one, so the KNN can extract much more information than the 2-point. Not surprising. We have the PDF smoothed at many scales. It's just, there's more information in there. There's nothing too new. We only have to use only a few of these functions. So here is, for example, a constraint on sigma 8. If I use the first nearest neighbor distribution, so the void probability function, if I use that one and the second nearest neighbor distribution function, the red curve, and a third one makes it tighter, but the fourth one almost adds nothing. So this is the particular density of points. It has roughly that much information that after 3 nearest neighbor distribution functions, you already extracted all the information. There's other fields that have more, that are more nonlinear. They will need more. But this particular example didn't need that many. And one can check that easily. It has a nice feature of being predictable. It's like all those things, anything that predicts the PDF as a function of smoothing scale, you can immediately turn into predictions for these. I showed you this Gaussian one. And there's some example code. I put the URL at the bottom that you can try this out for yourself. And yes. Yeah, and then there was an example. Christophe Pichon sort of turned me on to this thing last Thursday about Levy flights, which I hadn't played with before. And so I put a little example notebook also into that repository if you want to play with it. These are sort of point processes where you draw, where it's a random walk. You go isotropically in space, but you draw for the chump distribution, you draw from a power law. So you can make really far chumps in these. And they make interesting looking density fields that have void-like things in them, sort of emptier regions. And so it's sort of a fun way to try this out. But it's sort of a simple example where I really measure like hundreds of nearest neighbor distributions. Each of them makes sense, and all of it you can immediately turn into a PDF. So next time you have a distribution with a bunch of points and you want to make a PDF, don't put it on a grid and then count your distribution in the cells. Just look at this code, follow the example, and you get all the PDFs for all the smoothing scales in one go. And I think you'll like it because you can do things like this, where as a function of the volume, I'm actually looking for the mean, the variance, the skewness is this one, and you can do the kurtosis, or all the moments, but extract them directly as a function of scale in one go, right? And so you have access to a whole bunch of information you didn't think you had access to, because you probably would have gotten the PDF and then tried to fit moments to the PDF. And you don't have to do any of that. And you already get, yeah, I think it's just really fun to use. Okay, 3 minutes. Very quickly, you can use it for map making because now it's at a single point. I did all my nearest neighbor searches. I can just look what's the expectation of having k-1 points in these volumes. I can get the standard deviation, then I can divide the standard deviation by my mean density, and you get a measure of the variance of the field on that scale. And here's a fun thing to contemplate. If you were thinking, oh no, let me first do a Voronoi tessellation that has more information, it doesn't. This is already all contained here. If I just show you 1 over the volume to the second nearest neighbor minus the volume to the first nearest neighbor, then you'll notice you pick up all these faces. These are the faces of the Voronoi cells making up your density field. So there is no point in making tessellations. They will not have more information. They will only have less information than this. And so here, just briefly, just to advertise a little bit and have a look at these different papers. The one I was describing is really just the first one. We can do very good cross correlations, and particularly when you have very few sources, the shot noise is really high. You're very confused about, do these two samples correlate? You can do a much better job using these techniques. There's for the simulation, people that really like in-body simulation, we did an estimate on resolution requirements, which is quite interesting if you're into that thing. We've been trying out a whole bunch of different bias descriptions, or the hybrid EFT style bias descriptions, but also HOD-based modeling, which we use in this paper, just to get ready of what to do when we have full data. In this particular last two papers, I think with work with Boriana here and Sandy, Juan, a postdoc at KITP, we're building a full forward model for this, so where we do the Abacus Summit light cones, then we have the masks for the different surveys, then we do fiber collision modeling on the whole thing. So once we have this full forward model, we can try out all these different summary statistics and really compare apples to apples of which one has a good amount of information, which one doesn't. And then this one's not on the archive yet, but it's a generalization of this whole thing to also do this on the sky and perpendicular to the sky. So now you get much information of the RSD effects, the redshift space distortions, and it's not surprising. We find a ton more information by splitting things up in those two directions. But the entire framework you're thinking about, no smoothing, just keeping cumulative distribution functions, it all generalizes to 2D. And I think, to me, I think the way to think about this is to extend it to higher dimensions, where it's also the luminosities, the colors, all the different properties of your samples make up these high dimensional spaces, and where we can very effectively estimate densities if you want. There's one way to think about it, or it's just these CDFs of just parts of these probability distribution functions. There's a whole bunch of other things that we're working on with different lead authors. I just put it there in case you want to have discussions on this. And let me then just say that, it's all related because we're just talking about points and volumes. So, there's nothing earth-shattering here. All I'm saying is we have a very practical, useful way to organize your data where you can get more out of it, and you don't throw away information by just counting pairs. And so all I was trying to make is that this way of thinking about it is useful. All right, thanks.
Questions? Dick?
Hi. Great fun. Key feature was having the same number of points you laid down. And I understood that mostly you've been using Poisson laydowns of the samples. But you mentioned in passing, so I'm going to get you to elaborate, the redshift space direction. You don't want to do the same thing. And then if you have a selection function, which is a shape, you also don't want to do the same thing. So I assume that given the number of papers coming out, you've thought about all of these things. So maybe you could expand on those 2 points. Yeah,
for sure. Yeah, excellent point, right? So this whole thing of in surveys, and I'm new to this, I'm really trying to catch up, been reading a lot of papers, but a lot of people try to design their samples such and their redshift binning such that they can avoid a few of those issues that you just mentioned, like the redshift evolution of the galaxies, the actual evolution of the sample density, and so there's many different style approaches that people have had to this, and it's always quite survey specific. And that's why I'm personally just thrilled that it is possible that we can build these full forward models now, where we actually model exactly all those nuisance parameters that we see the survey has, that we model them, and can do this for 100 different cosmologies. So we literally can create a fake universe with all the systematics that we can spell out, and only the known knowns, obviously, like all the things that we've modeled. And so they are, so then in that space, once you have that fake universe, you can take care of every one of those systematics you were thinking about. Different N of Z's, different slopes, even quadratic bits, color biases. And I think that's really the way to approach this problem, at least now that we're not measuring the 2-point function, we're measuring the best fitting model, and then we can talk about what sort of statistics does that model have.
Can I make just one more quick comment? I was very pleased to see in your opening list, you highlighted Zapudi and Zale, which they were using the random and all that to do Zeiss, and it's related to that. It's different, but it's related to that. So it's good to highlight that important work.
Right, yeah, it's so fun that we're actually here together at the workshop now, yeah.
I'm just trying to understand how what you're doing is different than the classical nearest neighbor in my head, where there's no random points at all. You just literally measure the distance between galaxy A and its nearest neighbor. And then the cumulative distribution is just a step function, right, with 1 over n for each step. So what's the difference here?
Yeah. So actually in that last paper I'm mentioning, we are also using that one. So we do the RD, which we call this one, the random data, and also the data. The data is fun because, yeah, Dressler, I mean, it goes way back, right? And everybody, when you want a quick estimate of what's my density, density on a specific galaxy, you pick a k, typically 5, maybe 8. And in the classifier literature, you find people really strongly arguing about whether it's 5 or 8. And we got rid of all of that in the sense that it's not a density estimator. We do all the densities in one go. And the key part is we stayed away from being density weighted. We didn't want to be mass weighted. We want to really do the volume filling thing so we get the void distributions. We also have sampling throughout the volume, not just where the galaxies are. And so for some of the cosmology stuff and the primordial non-Gaussianity things, I think that's a big useful feature, that you're actually doing the PDF, not a density weighted PDF, like you do. What you're used to is a density weighted density estimator, right? Because you start at each data point.
So let me ask the same question in a different way.
All right.
So you have these very smooth cumulative distributions because you can have as many random things as you want, but there's still n galaxies.
Yes.
So there's still actually
exactly. There's a sample noise, there's a
uncertainty
Poisson noise, exactly.
Okay.
But that's the whole point that I love about this, actually. When I only have 3 galaxies, my measurement is totally fine. Like, I have no extra shot noise for my measurement. It's like, I don't depend on how many data points there are. So now it's going to be a very funny looking CDF because all the point, there's only 3 possible galaxies. Any point can be the nearest neighbor to. So it's just these spherical 1/r² shapes that are made by those 3 points, but it characterizes that field exactly, right? So if now in my theory space is like, what type of distributions do 3 points make? Like, I'm not confused. So I can always do this measurement. Or if you do 1, it's even more fun. You just get the 1/r². You're like, oh, wow.
Okay, let's talk afterwards.
Sure, totally.
Yeah.
Any other question? Okay, Ravi.
So it's a quick question. This is sort of asking the question about nonlinear versus linear. And so if I was doing the first nearest neighbor and I had lots of particles, the nearest neighbor is going to be like a parsec away or whatever it is, super close. There is no linear information in that naively. Right? Most people are cutting up k of 0.3 or
right.
Right? So what's going on? So in the counts and cells, it's a volume integral. Is it that the volume integral of the correlation function is actually getting most of its information from the linear k modes? Or is there, what gives, right? At what point?
Right. Yeah. So in your PDF version, right, this is now crazy low density. In the sense, you picked a tiny little volume and then you went around and you found no galaxies in it. Like, you had a parsec-sized sphere, and no matter what you did, you never had a galaxy in it. It's just so small. So now that's in that particular case. Now all that information would just be at the much highest K's modes. So now there's multiple levels I can answer this sort of more theoretical, but let me give you a quick practical one that's curious, is where often if you are particularly interested in, say, the BAO scale, because what you could do is actually first downsample your huge number of galaxies that you have, so that the mean density is exactly the BAO scale, and then your first nearest neighbor distribution all of a sudden is again super telling. The nice thing with this downsample is that you can reuse, you can downsample a billion times, right? Like, so you lose nothing in it. And the assumption that is built in here that you have a Poisson sampling out of a smooth field gets better and better the more you downsample. So that statistics, you can apply very well also on this highly
so that's
density.
effectively what I was asking Arka, a similar thing, right? Was that, are you basically downsampling to get a scale that is linear? If you didn't, then you
right. I mean, it really depends on what we're doing. Like, I mean, many of the surveys, they're not that dense actually compared to where our theory is. And so, but it depends on your theory prior of what sort of scale cut you still want to analyze. And so all I'm saying is, if you want, you can downsample to pick the scales that you're more comfortable with, but it's not a thing that is intrinsic to the statistic.
Thanks.
So
Right.
that's what Ravi's asking.
Yeah, I mean, of course, in this whole idea about nearest neighbor density estimation, is very close. I mean, so all that stuff is very close. Kernel density estimation too, and this is a very specific kernel density estimate. It's just a top hat that we're using, and so there's many connections to other things that you might be thinking about. And yeah.
Yeah, I mean, I think the
Sorry, Doc.
samples you've got have
Sorry, Doc.
distances that are
No more
similar
time.
to
We have to
linear.
stop now. So let's thank Tom again.